So yes, I'm here to tell you about ACCESS's new ice sheet model, ISSM, which is the ice sheet and sea level system model, and a little bit about the process that we developed to make a decision on an ice sheet model to support within the NRI. But first I wanted to start by talking a little bit about the case for ice sheet modelling in ACCESS, and where we're at, I guess, in our understanding of some of the coupled interactions between the ice sheets and other components of the Earth system. So unlike many of the other components of ACCESS that we're all working on here, ice sheet modelling is actually a relatively new field, and the first continental scale Antarctic ice sheet models were published in the 90s. And at that time, the pervasive view really was that ice sheet models are relatively slowly evolving components of the Earth system. The models were developed for glacial to interglacial cycles, and that was kind of reflective of the fact that we were using the shallow ice approximation to the Stokes equations, which really captures that diffusive response of the ice sheet to kind of long timescale climate forcing. There was evidence at the time, and many decades earlier, that kind of suggested that the ice sheets were much more dynamic and responded more rapidly. But the early models that emerged in the 1990s were really these kind of slow-flowing ice sheet models. But of course, our understanding of the role of Antarctica and Greenland and ice sheets generally in the Earth system has evolved a lot since then, spun off by the satellite era and the kind of high-resolution data that we're seeing coming out by oceanographic measurements. And I'm sure there are some in the room who over the course of our careers have even seen such a change in what we understand about how ice sheets are interacting with the Earth system. And ice sheet models have advanced considerably. We have the capability now to capture crystal to crystal evolution, and what that means for the large scale deformation of the ice sheet. We can run regional configurations that capture crevasse fields, maybe not exactly looking like this at this kind of detail, but our understanding of these kinds of processes are being resolved a lot better in ice sheet models now. And then of course, we have continental scale ice sheets that we use to make projections of how sea levels might change in the future. And this is a very Melbourne-centric talk, I'm sorry, but this is an image from earth.org which shows coastal flooding at 2100 under mild and extreme scenarios of sea level rise, and you can see that about 80,000 people are likely to be impacted by projection or changes in the sea level in coastal regions of Melbourne by the end of the century. So we know ice sheets are important, but do we really need kind of fully coupled interactive ice sheets that capture interactions between the ice sheet and other components of the Earth system? And I hope that I don't have to convince you, but I'm going to try anyway. And that, of course, has become more important given that we're in a climate-changing world. And oceans have absorbed over 90% of the additional warming in the Earth system. The Southern Ocean alone is absorbing about 2/3 of oceanic anthropogenic heat, and of course that has impacts on these large-scale overturning circulation. And if I use an analogy that has been used previously, the Antarctic ice sheet and the Greenland ice sheet are like the heartbeat of this global overturning circulation, and we really need to be able to couple ice sheets into the Earth system for you to be able to capture that. This was demonstrated really well in a recent paper that looked at the impact of freshwater flux into the ocean. And you can see in the orange line there, when you incorporate, the top panel, when you incorporate freshwater fluxes from the ice sheet into an ocean model, we see that there's a decline or a contraction in the production of Antarctic bottom water compared with when we're not considering freshwater fluxes alone. And it's not just this one-way interaction, right? It's not just that the ice sheets are melting and there's freshwater flux into the ocean. It's actually a two-way feedback, and the changes in the bottom water formation actually impact the supply of modified circumpolar deep water onto the continental shelf, which is the water mass that is driving the loss of ice in Antarctica, particularly in the Amundsen Sea sector, but also in East Antarctica. So we really need to be able to capture those two-way feedbacks. It's a similar story in the northern hemisphere when we're thinking about the interactions between the Greenland ice sheet and AMOC, but actually it's a bit different in Greenland. And since the 1970s, we've seen that about half of Greenland's ice sheet mass loss is driven by atmospheric interaction, so warm atmosphere melting at the surface, and about half is due to dynamic thinning, so the glacier response to changes in ocean forcing. But there's research that demonstrates that it's not such a clear-cut picture. And this particular piece of research by Slater and Streneo a couple of years ago showed that what happens is we get atmospheric variability, which causes surface meltwater ponding. That surface meltwater can make it all the way to the base of the ice sheet through these big moulins, like rivers internally into the ice sheet, and then they lubricate the base of the glaciers. We then see surging, so speed up of the glaciers, which of course delivers more ice from on land into the ocean. But then you also get these plumes of subglacial discharge, which kind of are buoyant plumes, and they melt at that interface between the glacier and the ocean. And even though the glacier is about 4 times more responsive to increases in the ocean thermal forcing, so increases in the change of the ocean temperature, these plumes are much more have like a much stronger magnitude, and so they actually have a relatively more, have a greater impact on ice loss than that thermal forcing from the ocean melting as well. And so this makes the case that it's really important that we have ice, ocean and atmosphere coupling at least. And then of course, when we think about the whole Greenland picture, we also are seeing a lot more extremes. That's the same in Antarctica. This schematic is from the 12 months from September 2018 to the end of August 2019, when there was really a lot of extremes which increased the atmospheric temperature over Greenland. We saw much more melting, and then of course the glaciers responded and surged, and we saw much higher mass loss. Interestingly though, atmospheric rivers are actually playing a really important role in surface melt and ice loss from Greenland, and punching beyond their weight, if you like. So even though atmospheric rivers occur less than 1% of the time in Greenland, they can account for 10 to 15% of the surface melt. And because they're likely to become much more frequent and more extreme, it's really important that we capture the impact of atmospheric rivers on ice loss. We don't really do that in the resolution that is available for most of our ice sheets, for most of the 2 ice sheets that we have. But again, I think it's a really important case, not just for ice-atmosphere coupling, but for high resolution, because we know that we're not going to capture the impacts of atmospheric rivers unless we can actually resolve them. And then what happens in Antarctica and Greenland doesn't just stay there. Of course, we have these large teleconnections throughout the globe, and I think that was really well demonstrated in this paper a couple of years ago that shows how contraction in the polar, or weakening of the polar vortex can actually play a really important role in the bushfire danger index. And so these plots here show the relationship between the forest fire danger index and the 9 weakest polar vortex years. Coming back to standalone ice sheet models now, we have seen, so we have the ice sheet model into comparison project 6, which has just done an enormously excellent job at increasing the visibility of ice sheet modelling and showing that it's really important that we're considering ice sheet models. And although there's somewhat good agreement in terms of the regions that we expect to see ice sheet mass loss over the coming few centuries, there's still quite a high degree of uncertainty between these models. And you can see that in the coloured squares in the zoomed-in regions in the panels on the right, which show the retreat probability. So that's measured by the number of ice sheet models that predict retreat into certain cells. And you can actually see that there's a really big spread, and that's indicative of the fact that there's a lot of uncertainty associated between the ice sheet models themselves and what processes they capture and what they don't. But then particularly in the Cycle Coast region, so around the Ross Sea and the Weddell Sea, it's really the climate forcing that's driving that. And so again, I think it's really clear that we need to better capture these coupled feedbacks. And then one final thing that I think is really a great resource if you're interested for teaching. I use this as well. We now can not only see that ice sheets are causing sea level rise, but we can actually look at where we're seeing mass loss and what's driving that. And so this shows that for Melbourne over the last couple of decades, about half of our sea level rise is coming from ice sheets and glaciers. And then we can see in the panel on the right where that's actually coming from. And so you can see that Greenland is driving the sea level rise in Melbourne. And of course, that's similar for the rest of the east coast of Australia. I'll come back to that later. I didn't talk about ice sheets and biology or ecology, but this is a really great resource if you're interested in knowing more about some of the coupled feedbacks, at least for Antarctica, a report that was released by SCAR a couple of years ago. Okay, so ice sheets are really important. We need to include them in our Earth system models. What did we as a community, how do we go about making the choice of what ice sheet model to include? So I just wanted to highlight the fact that this was a group effort, and I really want to thank everyone in this room and not in this room who participated in this process. It was your support and your help and the time and energy that you spent was really, really enormous and helped us to make a decision. So this process, I guess there are two kind of things that I wanted to highlight about how we went about it. And one is that we really wanted the choice to be purpose-driven. We wanted to choose a model that was fit for purpose and that would serve the needs of our community now and into the future. And so we derived this purpose here, which was to facilitate improved decadal to centennial scale projections of global mean and regional sea level. And another thing that we wanted to do was make sure that the process was open or inclusive, transparent and rigorous. And so hopefully you all saw on the Hive Forum that over the course of the process we were providing a lot of materials of where we were up to and asking for your input, and thank you for those who responded to that. Okay, so I'm going to walk you through the three main stages of the process that we developed now. The first one was community consultation, which included identifying candidate models and then defining an assessment approach. So we assembled a list of 15 ice sheet models that are used globally. And to make it onto that list, you had to satisfy one or more, three things. One is that you may have been a model used by people within Australia. The second is that you may have been a model that is being included into a coupled Earth system model. And the third thing is that you had a large user group, and by large that means at least 6 people. We then developed 28 selection criteria across 5 different categories. And these were accessibility/community, so we're talking about what's the user base, how open is the development plan, how does that work within the Australian community, for example. Flexibility and modularity, which also includes not just kind of some things around the numerics, but coupling with other components of the Earth system. Input and output, including initialization methods, and you'll see in a few slides that that's really important for ice sheet models. And then model physics and model capabilities. From these 28 selection criteria, we designated 13 as essential. That is, to meet our aim of being able to produce decadal to centennial scale projections of sea level and climate change, we really need our ice sheet model to do these things. And then we used these essential criteria to develop a shortlist from that original 15 models, and it turns out there were 3 models that satisfied our essential criteria. We then went through an assessment stage. So the preliminary phase of that was to compile as much information as we could on each of our 3 shortlisted models against each of the selection criteria that we had. We then contacted and had quite an in-depth consultation period with the developers to provide more information, particularly where data weren't published. So, what's on the horizon for development in the next 5 to 10 years? We don't want to exclude a model because it doesn't meet one of our essential criteria. If it turns out that that is about to happen. So actually, that developer assessment was not just the 3 shortlisted models; it was all of the models on the 15 ice sheet model list. And then the third stage in the assessment was a community assessment, where we asked for your input on all of the information we collated to develop a preliminary ranking. And the final stage of the process was that we got a bunch of experts into a room together to look at all of the information and to also conduct a risk assessment, so looking at things like organisational risks, financial risks, political risks, etc., to make a recommendation for the board on one ice sheet model to include within ACCESS. And the recommendation went through in June this year and was adopted by the board. Okay, so I just wanted to give you a couple bits more information on those 3 shortlisted models. This is the table that is the result of the community assessment process for our 3 shortlisted models, ELMA, ICE, ISSM and ICE-PAC, against each of the 5 different categories of selection criteria. And I'm not going to go in too much into the details, but what we found was that one of the models, ICE-PAC, didn't quite meet what we were looking for. And that was really because it's quite a young model, I think it was released like 2 or 3 years ago, and so it didn't have kind of that long track record of that the other 2 models we were looking at did. Although I would say ICE-PAC is a really great model, and I think some of the capabilities that it has are really exciting, particularly if we're doing kind of process-based studies. So, if you're interested in ice sheet models, I'm going to recommend the one that ACCESS adopted naturally, but ICE-PAC is very cool. We didn't see that there was enough of a difference really between ELMA, ICE and ISSM in this community assessment evaluation to be able to clearly say one of those was a winner. So we had to look in a bit more detail at the differences between the 2 models. And so in the expert panel meeting, we looked at these selection criteria where there were kind of key differences between the 2 and made an evaluation based on this. And ultimately, it was ISSM that was recommended to be included within ACCESS. So I'm going to give you a bit of an overview now of ISSM, what it does, and a few kind of case studies from research within Australia. So it's 10 plus years old, and there's a really active contributors to the development of ISSM around the world, including a user base of over 150 people, which is pretty good given that the ice sheet community is actually quite small compared to the rest of the climate modelling community, and 4 active users within Australia. So the ISSM incorporates the Stokes equations, which are the most complete representation of momentum balance, as well as multiple approximations, including depth averaged approximations, so we can run at much longer timescales. A range of options for things like sliding laws and flow laws that are really, really important to capturing the dynamic response of the ice sheet to changes in the atmosphere and the ocean, and also an anisotropic, static and transient adaptive mesh. So to illustrate that, I've got a plot on the left of like a typical anisotropic mesh with no adaptiveness, and then on the right I've used the ice sheet surface velocity field to actually adapt the size of the mesh, each mesh cell based on that velocity field. And you can see that the mesh size is obviously much smaller where the ice is flowing much more rapidly. And this is really, it's absolutely critical that we have fine resolution near that grounding line, which is that zone between the grounded ice sheet and then the floating ice sheet. Most of the important stuff happens there, although not all of it. And so we need to be able to capture that, not just where the grounding zone is now, but how it's going to evolve into the future. And so capturing an anisotropic transient mesh is also really important. Most of, I guess, the publications that we've seen in the ice sheet and sea level system model are kind of decadal to centennial timescales, although we might conduct millennial scale spin-ups or initializations. But we do, and they incorporate both continental and regional scale configurations, but there are a couple of examples of longer simulations, and this is an example of one that simulated parts of the Greenland ice sheet over the Holocene, and you can see that there's actually pretty good agreement between the model ensembles and broadly what we think the ice volume did over the Holocene in that top line, particularly towards more recent, that few thousand years. Another thing that's incredibly important in ice sheet modelling is the initialisation procedure, which I mentioned before, and this is because the trend, like how ice sheets are trending, surface elevation changes, grounding line changes, over the last few decades to centuries, will play a really important role in what the ice sheet does in the future. And so one of the best ways to be able to capture those trends is to use what's called the control or the adjoint method, which we use to solve for really important unknowns like the basal friction coefficient at the base of the ice sheet where it comes into contact with the bedrock below. And so ISSM has the control and adjoint, and you can see the estimated basal friction from inversion on the left there. Another thing that's really cool that ISSM incorporates, and you can actually watch a talk that we had at the Crisis Modelling Working Group last week by Mathieu Morlegam, who developed this in ISSM, is automatic differentiation. And basically, automatic differentiation calculates the derivative of any field with respect to any other one. So you can kind of backwards propagate and look at sensitivity analyses. So rather than having to run like really large ensemble where we say what happens when you change one parameter to another parameter, like basal melting from the oceans to ice volume over time, instead of having to run a large ensemble, we can use automatic differentiation to directly test that sensitivity. And this is a plot on the left of the sensitivity of the volume above flotation to surface mass balance, and on the right, the sensitivity of volume above flotation to the basal melting. So basically what this is saying is for 1 unit change in basal melting, what does that do to our volume above flotation? And you can see that melting in the shear margins of Pine Island Glacier, which is this glacier here, in the shear margins, the melting, when melt is concentrated in those regions, the ice sheet's going to respond is much more sensitive to melt in those regions. So this is a really kind of excellent way to approach it, although it is linear, so we're not going to capture non-linearities in between processes. Another thing that AD enables us to do is transient calibration, which basically says, can we optimise unknown fields over a long period of time with running the ice sheet model to match trends. And it turns out that transient calibration is exceptionally important to being able to capture future evolution. And Mathieu's talk again, which is on the Hive Forum, does a really good job of showing that these glaciers in the Amundsen Sea sector are very sensitive to how well your ice sheet model captures what's happened over the last few decades. And then finally, I mentioned the sea level fingerprinting capabilities of the ice sheet and sea level system model. And I guess I'd say here is that it's not just the ice sheet and the climate that's important, but it's what's happening with the solid earth as well. And so these plots here show for an uncoupled, no kind of feedbacks with the sea level or solid earth processes on ice sheet mass loss, and then each successive panel shows the incorporation of another solid earth feedback. So for example, the fact that when you remove ice, the solid earth rebounds. And the most complex is that NSM, which I'm not going to go into, but you can kind of see what they do with each of the feedbacks in the schematics. But importantly, what we find when we incorporate these solid earth feedbacks is that they actually, as a whole, are a negative feedback on ice mass loss and can reduce estimates of sea level rise from the Thwaites sector or Amundsen Sea sector by 10 to 15%. So just 3 more slides on some work that we've been doing in Australia using ISSM. And so this builds on what Andy mentioned earlier on detection and attribution. And so Johanna from Monash Johanna Beckman is leading this work from Monash, and we're working in collaboration with folks from IGE in Grenoble who use Elmer Ice to actually backpedal to 1850. And the challenge here, which I'm not sure, to me, I'm like, whoa, what did the ice sheet look like at 1850? And actually, we don't really know. So it's that getting back to an 1850-like state is a very big challenge. There are some estimates of where the grounding line may have been. There are some estimates of how rapidly the grounding line might have retreated. But nevertheless, Johanna and Justine, who are leading this work, have made really great progress in getting back to that state so that we can start to see how anthropogenic climate change has impacted mass loss since then. And so currently in the kind of final stages of this, but the idea is to run really large ensemble from that 1850-like state to 2100 using anthropogenic plus natural variability forcings and natural variability alone. But these configurations also enable us to say, things like how much does that trend matter, and what does that mean for how we as an ice sheet modelling community can improve our initialisation procedures. Some recent work that we also have been involved in is the role of ice sheet modelling and subglacial hydrology. And so this was a paper published, led by Tyler Powell, that was published earlier this year, where we coupled the ice sheet ISSM with a subglacial hydrology model. And what this research showed is actually you really need to consider these feedbacks between the subglacial hydrology and the ice sheet to be able to capture not just how rapidly the ice moves, but enhancement of the ocean-driven melt. And so you can see in that sea level contribution panel on the right that when you include subglacial hydrology, you can actually increase your contribution of sea level by, again, 10 to 15%. And then finally, we've just had submitted the first whole Antarctic subglacial hydrology model from the ISSM version of GLADS at 40-metre resolution. It shows large lakes and long channels, and there's a very good agreement between what this model configuration shows in terms of the location of lakes and where we expect to see lots of subglacial discharge. And this is going to be really important for initialising kind of whole ice sheet subglacial hydrology models. So if you're an ocean modeller and you're interested in discharge and what that might do for plumes, this should hopefully be out soon. So I'll leave it there. What next? Mike Tetley, the new ice sheet modelling team leader, has a poster today, although he's unfortunately not able to be here. We have our workshop on Thursday. Please do get in contact with us if you want more information about where we're at, or if you want to collaborate. Hopefully we'll have a coupled model in the next few years. And finally, a huge thanks to the whole Cryosphere Modelling Working Group and everyone who participated in our process.
Thanks, Felicity. Dave.
Me again, sorry. Just what's the timescale, do you think, on getting this into like a coupled mode with ACCESS-ESM or ACCESS-CM2 or something?
Great question. I might be able to have a better answer for you in the next couple of weeks. So ISSM has been coupled with with the MIT GCM, and so there's like a really clear framework for that. MOM6 also we'll be working with, one of the ISSM developers actually just moved to GFTL and is working on the ice ocean coupling with MOM6, so there's a really clear pathway there, I guess, and also given the expertise within the community. The atmosphere side of things, we can of course work with people from Reading who are doing ice sheet model coupling. Some modelling centres around the world who have done ice sheet ESM coupling, it's just taken a very long time, and I'm hoping we can learn from their mistakes. It would be great if we came to something in the next 3 to 5 years, and that's the aim, 3. But yeah, we'll see.
Do we have any other questions? Yeah, we'll go to Gemma next and then up there.
Thanks, Felicity. Quick question about observations. How much do things like our current bathymetry estimates over Antarctica and other observations we could make now but may not have impact our assessment of what the ice sheet's doing?
They have a huge impact. So one thing that I'm currently working on in East Antarctica is like the impact of bathymetry. So we've got an ice-ocean coupled model of East Antarctica to the Totten region, and the bathymetry matters enormously, and you can see like 3 to 4 times increase in basal melt rates due to how well you resolve your bathymetry, particularly where we have found in recent years that there are these huge troughs that we hadn't previously mapped. Yeah, it's wildly important, and as much as we can do to improve like bathymetry and ice sheet topography, particularly in the region of the grounding zone, is like, it's absolutely fundamental. Yeah.
Do you get auto differentiation functionality across the full set of physics in ISSM? Or is it only just like a core, kind of the core physics routines?
What do you mean, sorry?
So the auto differentiation functionality in ISSM, yeah, often it's easy enough to implement these things in like some core routines, but like the full suite is quite difficult to do. Do you get like, well, all physics active in ISSM, you still get auto-diff functionality?
With automatic differentiation, you mean?
Yeah.
Yeah, we don't run that. So usually we'd run that for initialization, but not for prognostic simulations. And it's incredibly expensive, but I haven't actually looked into that. So yeah, maybe this is something that we could have a chat about.
I think we've got one more question.
Yeah, Felicity, you got a quick question. So when you mentioned about this ISSHEET model and the response of solid Earth, so are you talking about you couple this ISSHEET model with the sea level fingerprint module?
Yeah, so the Leroux paper incorporates all of these feedbacks. So so this is a module that you can run for projections, and that's what the plot on the right shows.
Yeah, that's a good way to go, yeah.
Yes, I concur.